Hello, everyone. It's nice to be here. Thank you, PyData folks, for calling me. Just a small note. This actually, I need to kind of know what everyone wants to do. Do you folks want to do the setup as well? I mean, do you want to set up your environments and actually do it yourself? So the reason I'm asking this is because I'll have to pace the rest. I have to pace the rest of my tutorial accordingly. So what I'm going to do is first tell you to look for me on GitHub. I am Bhargav Wader with 2 V's, like Darth Vader. I made that a long time ago. Don't judge. Yeah.
You have a volunteer here. If you need to carry the microphone, I'll just let you run the session however you run it. If you want to take questions, take questions. If not, don't.
Okay, sounds good. Awesome. Yeah, so please try and find me, and once you find me, go to my personal Jupyter notebooks, which is called Personal, and you should come down to here, which is personal/notebooks/text analysis tutorial. So I'm going to give you just a minute to find this URL. Take your time. Once you get here, which is, I suppose, a minute, I'm going to ask you some questions again. Okay, so this makes things easier. Since the network is congested, it means that it's highly unlikely you folks are all going to find the page, do the downloads, and do everything. So what I'm going to do, and this is extremely, extremely important, please note down this URL, because it would be really cool if once this is all over, you could go back and actually set up your environments on your own, on your personal machines later. But a huge part of this tutorial is you folks all going back and doing text analysis later. So please take your time down to get this repository and this particular URL. There are multiple Jupyter notebooks, multiple tutorials, resources, links, and a bunch of things which will help you in life and text analysis. So take maybe a minute to just make sure you find it. Yeah? Yeah, of course. Shit. Hold on. So are you having trouble looking at this? Or I'm afraid I don't know how to zoom in on the URL. Is it still a problem, or can you have a look? Just to help you find it, it's github.com/Bhargav Vader. So like once you find this over here, this is my GitHub username. If you go to github/this, it should be fairly easy to find personal. So again, I'm just going to give like 2 to 5 minutes for you to find this repository and for you to find this link before I continue. So that's like 2 to 5 minutes. I'm sorry? Is it like, does no one have internet then? Okay, that's, okay, so what I'm going to do is, okay. So can everyone see this URL over here now? Just at least note this URL down on your, take a picture of it or note this URL down even if you don't have internet. Just take this down, github.com/ that particular one. So even if the network is down, even if you cannot log on to the internet, you should have this. It's 9.3, I'll wait till like 9.5 and then. Okay, it's 9:05, so I'm hoping everyone has settled down more or less. I will, of course, at the end of the tutorial talk about the link and all of these things. Just to make it very clear why I'm so particular about this is because normally a huge part of the tutorial is walking everyone through setting up a virtual environment and setting up the packages required to do text analysis. Of course, having Anaconda or having your virtual environment already set up would mean this would be normally very straightforward. But this is a very important part of the tutorial because I would like I said before, I would really like everyone to go home and continue doing their text analysis. So just a point before I actually start talking about what we're going to be doing. This link has, like I said, all the material, both reading material and code, which you would need to get started on your own later. And it would be really cool if everyone could check it out later. And, you know, it's a GitHub repository, so of course, issues, pull requests. If you have any problems, suggestions, anything, then it would be incredibly useful. Okay, so we're going to start now. And in this tutorial, I mean, like the name of the tutorial, it's a text analysis tutorial. I call it Topics, Tricks and Tips in Text Analysis. So one thing to make clear, I will not be going so much into depth. I would rather be going into breadth. I'm going to be talking about why you should do text analysis, why you should do it in Python, and what are the different kind of things which you can actually do. I just want to give you a taste of all the cool things you can do, and once you have a taste, you can actually go and cook your own stuff up. You can figure out which part of text analysis appeals to you, which part of it could be useful for your personal work, your research, your business, and you can actually get started. But overall, I'm just going to try and give you a motivation of why text analysis is really cool and also really important. So one thing I would also like to specifically talk about is the libraries and packages which we will be using. Why this is important is because I want to focus on industry standard or industry strength code. We are not going to be writing sloppy academic code which no one is going to look at later. I mean, you can still write your sloppy academic code. It's just that if you'd want to get anything into production, and if you want to move out of sandboxing, then you're going to be needing the tools I'm going to talk about. For example, one of my pet peeves is NLTK. Most people, when they think of, we're going to do some natural language processing, like, let's do NLTK, let's bring out, I react to that horribly. I say, no, absolutely not. You should really stop using NLTK. NLTK is academic code. It's bloated. It has a lot of things which you are not going to be using. And honestly, it's really not as well maintained as other packages out there are. So that would be one of the first examples of the kind of methodology you'd want to follow. So stop using packages which are academic and bloated, and use more efficient packages. So a huge part of what I'll be talking about is a package called Spacey. Spacey is, I believe, written by folks from Berlin, actually, and by Matt Honeyball and Ines, who've done a great job with the library. It's really fast. It has a lot of nice features, which I think which eclipses NLTK in terms of the best possible way to do a certain task, and I cannot recommend it enough. So that's another part of it. We'll be importing Spacey as well. So Spacey is used for the computational linguistics and the pre-processing part of our code. Then we're going to be using GenSim, which stands for Generate Similarity, which is a really popular text processing library as well. We're going to be using it for topic modeling. I'll be getting into what topic modeling is in a bit. Then we're going to be using, we're going to be using Keras, which some of you might have used before or heard of. Keras is a deep learning or a neural network-based library, so we'll be using Keras as well. And we'll be using scikit-learn, which also most people who work with data at some point would have heard about before. So this is just to introduce you to the kind of tools we'll be using throughout the tutorial. We'll be running it on a Jupyter notebook. We'll be using Python. And that's pretty much it. So, that's pretty much it regarding the technical infrastructure of what we'll be doing. Now, about text analysis. Now, one of the particular reasons why I really enjoy working on text analysis is, the personal nature of the data. It so happens, for example, sometimes when you're working with, like a normal first thing which people work on in machine learning might be the iris data set, where you have to classify the iris data set into the 4 different kinds of flowers based on, the petal width and all this stuff, which is, it's cool. I mean, you're, using the width of your petals of your flowers to decide what kind of flower it is. But honestly, I could not care less about these flowers. And the reason why I started doing text analysis is because I wanted to be personally involved with the data I was working with. And what's really cool about text analysis is you can actually use your own data. You can use your own Facebook messages and WhatsApp messages. You can use your own emails. You can use, if you like a particular book and you happen to have illegally downloaded off the internet, do not do that. But if you did, you can analyze that as well. It's really cool, the kinds of things which you can do with text data and personal text data, which is my usual motivation behind telling people why you should do text analysis. You can do really cool things on your own. But, of course, why to do text analysis is a talk of its own. I mean, what I want to, of course, get into now is what we're actually going to do. So we're going to start right now. Please feel free to stop me if you have any questions. What I'm going to be doing is just running the Jupyter notebook and talking about the code. So honestly, even if we did have internet, what you would be doing is pressing enter with me. So you're not really missing out on too much by not having the Jupyter notebook. I just like everyone to have it because it gives you a sense of accomplishment and it's nice to see the results. But it's still okay. We're still going to learn a lot and have a good time. But again, like I've mentioned before, follow my link and please download this for yourself later when you go somewhere where you have internet or back in your homes or whatever. So, okay, let's get started. So like I mentioned, what exactly we'll be focusing on is the entire pipeline of text analysis. I want to walk you through, actually getting your data to the kind of things you can do. A note about getting your data. Okay, I actually have an actual note on it. Okay, so let me just start my imports. So I talked about some of the packages before. These are the packages we'll be using. So we're using Theano to power our keys. This node is for keys. I don't want to listen to warnings at the moment because it makes the notebook not look as pretty. And also want my plots to be inline, so I'm doing matplotlib inline. Gathering data. So a huge part about text analysis in general, like I mentioned before, is the personal nature of data. Now, it's kind of mean of me to talk about how fun personal data is and then after that use a newspaper corpus, because that's what we're doing. But one of the main reasons is because when I actually started doing the tutorial along with the data gathering part, it ended up becoming a really, really long tutorial. I honestly think you can spend an hour and a half on just gathering your data. One of my favorite places to gather data is Twitter. Mainly because it's a lot of rich textual data. You have a lot of data. I really like using Reddit as well for gathering data. Reddit's API is also pretty neat. And the thing about Reddit is because it's JSON text, which is structured. Reddit is a news aggregation website where you can find news links and not just news, all kinds of entertainment and links. But you can find in the comment section, there's quite an active comment section, you can find lots of structured questions and answers and replies, allowing you to really get rich internet data really, really fast. So these are some of the places you can actually gather your data from. I've also talked about using your own personal data before. For example, in WhatsApp, if you hold down your conversation, you have an option to email the entire chat to yourself. So you can email the chat to yourself and start analyzing your WhatsApp conversations. So these are some of the places where you can collect data. You can use Beautiful Soup to actually, mine websites and get data off, actually using website data. So there's many ways you can gather data, and a huge part of text analysis after gathering your data is pre-processing. Now, pre-processing is super important in, of course, any kind of machine learning or data analysis, data science kind of job, but in text analysis it becomes extremely, extremely important. You're all going to see why it becomes so important in just a small bit. But as for now, a little bit about the corpus. One of the corpuses we're going to be using immediately. It's the Lee background corpus. It's newspaper articles, 300 of them from 2000 and 2001. It's an Australian newspaper agency. So the news is going to be focused more on Australian news, but a little bit of international news as well. The reason why we're using this data set is because it's easy to use. It's on Gensym, so all I have to do is, as long as you have Gensym installed, you can easily load the data. It's easier for me to show you examples of the things we can do if I use this data set. Personally, I don't like this data set because it's kind of depressing. News in 2000, 2001 was kind of depressing. So, but this is what we're going to be using for this data set. You can always use your own data when you actually try this out later. So that just loads up your data set. It's basically, I'm using the Gensym pad to find the test data, and then after that I'm downloading it. Again, if you have any doubts, If you have any doubts regarding any lines of the code, please do stop me, or if something is not clear. I talked earlier about why you should use spaCy and not NLTK. One of the first things which you do in text analysis is, like I mentioned before, pre-processing. And one of the first things which we do in pre-processing is getting rid of something called stop words. Stop words are basically words which we think don't add any information to our final results. So one of the things which we do is before, for example, words like articles, like this is of course in the context of English, but I would like to note that most, or if not all, most of the things I'll be talking about is of course extended to German, to French, to most modern languages. So stop words are words which are not going to add any useful information to our results, so we'd want to get rid of stop words in different ways. Now, to give you an example of how NLTK would have done this, NLTK allows you to import an entire list of stop words. So you have a massive list of stop words, so you add, you just import this list, and then you can actually add words to this list by, however we add, like just appending words. And what you would do is you would go through your entire data set, and you would say, if the word is not in stop words, add this word. So you'd actually go down, this is how you would do it with NLTK. Now, the cool thing about spaCy is spaCy, and this is actually the main selling point, and I would argue this is one of the most important parts of this tutorial, is spaCy uses something called language models. So what a language model does is it basically processes your text. Now, when it processes your text, it does many, many things to it. One of the things it does is identifies what stop words are in your text. It identifies which one of your letters are numbers. It identifies which part of your text is punctuation. It identifies it identifies each of your sentences separately. It identifies your documents. It tells you, for example, if you'd want to find out which words in your sentence are verbs, it has that information as well. Now, the best part about this is, for example, if you were doing the same exact thing with NLTK, you would need a part of speech tagger, for example, and you would run this part of speech tagger on your sentence, and then it would tag it, and you would print it. So you would have, for different processes of your text analysis pipeline, you would have different tools which you would pick from NLTK. By the way, when I'm talking about NLTK, I mean any other tool which you can use. So you'd pick out different kind of tools for different kinds of tasks, and you'd use all of them, and this is not always the best thing to do. It's nice to have one pipeline which does everything, and this is why spaCy is super, super cool. With just this bit of code, NLP is equal to spaCy.load.en, you are doing a lot of things. What exactly is going on? When I do spaCy.load.en, I am loading spaCy's English model. For example, if I was working on German language text, I would use spaCy.load.de in quotes. There's different ways to load language models, and you can actually just search spaCy language models, download for different ways. I have links on the repository as well. But you would first need to download a language model based on how complicated or intense you want your language model to be. It can be 45 MB to even a GB. So depending on what exactly you want to use your language model for. So you'd start out with downloading your language model, which would be pip install, whatever, or you can actually do spaCy download the name of the language model. So based on how you want to download it, you would download your language model. Once you download your language model, and it'll be in the same directory as your spaCy, if you'd want it to be the same directory as your spaCy installation, and you would do this. NLP is spaCy.load.en. And there we go. We have now NLP is what we would call our pipeline. So I would call NLP by pipeline, which I've loaded from spaCy because I did EN. It's my English language pipeline. I talked about stop words earlier. So the way spaCy deals with stop words is when it analyzes your text through its pipeline, it annotates or it tags different words as stop words. Now, I've done this experiment on this particular corpus before, so I know for a fact that the words which I've mentioned over there are stop words or words which I think do not add useful information. For example, it's a newspaper corpus, right? Which means that you're going to have a lot of people saying, Mr. So-and-so said something about something. Now, words like Mr. and said are not useful information to me if I want to find out unique words or special words in my corpus. So you notice how I add says, saying, I mean, different variations of the word said, and today and Mr., so that I want to ignore these words as part of my final analysis. You're going to probably understand a bit later about why exactly I'm doing this. For now, you're going to have to take my word for it that these words do not add any useful information to my results, but I'm going to come back and show you exactly why. The reason I put this code over here is for you to have a look at how you, in Spacie, how you add an extra word to your stop word list. So what we do over here is for the stop word in my list of stop words. Lexeme is the linguistic unit which Spacie converts each word to, and I basically say lexeme.isStop, which is it a stop word? It's true. So I'm basically forcing Spacie to consider all of these words as stop words. Yes?
Doesn't Spacie know that said, and say are all the same word?
Okay, so that's a very good question. The question is, doesn't Spacie know that all of these words like say, said, says, and saying, especially these 4 words, right, because they have the same root? Yeah? So doesn't Spacie know that they're all the same word? Yes, it does, and I'm going to explain why I would still need to do this in a small bit. We're definitely going to talk about it. Yeah? So right now I'm just going to add these words, and now what I'm going to do, and this is the really important part, is I'm going to actually process my entire text using my pipeline. So just a small reminder, text is what I loaded off the GenSim, which is my corpus. So here text would be whatever personal data you want to use if you don't want to use the newspaper dataset. And what I'm doing is my document, which I'm going to contain my Spacie document, is equal to NLP of text.lower. Now, text.lower over here is a personal choice because I don't care for punctuation in topic modeling, which is what I'm going to show a bit later. So I did text.lower. If for you, for example, if you need punctuation or if you need capitalization, then you do not do text.lower. For me, I needed to do it, so I do text.lower. This is a computationally intensive part of the code because you're actually, so when I'm like running this cell, this is magic. This is super cool. This is very fun. So what's going on is I'm actually passing my entire text through my Spacie pipeline. NLP, just a reminder, NLP is my Spacie pipeline, text is my text, and there we go. So this takes some time, but yeah, so what's going on over here is, like I mentioned, yeah? Load doesn't work. So the instructions to download the file are actually on the page which I talked about earlier, this page, like my GitHub, this. Yeah, and the other thing is, it's pretty much one of the first things you do when you download Spacie is you download Spacie and then you download the language model which you want to use. So for example, if you're working with English or German data, the first thing you do is pip install Spacie, and once you pip install Spacie, you would do Spacie download en. And these instructions, yeah, okay. So I've actually mentioned downloading Spacie language model over here, so. Okay, it's awesome. So you can see in the 6 Jupyter, doc is done, which means now, technically, these first 6 lines of code are one of the biggest takeaways from this tutorial. It doesn't seem that impressive, but honestly, it really, really is. Learning, just how to set up Spacie for your personal text analysis projects is really, really useful. So what exactly happened? Let's look at doc. So you can see, for example, in the first document, hundreds of people have been forced to vacate their homes. Everything is, of course, in lowercase. These are newspaper articles, and you can see that each over here, there's a new line. Each new line is your new article. There are 300 articles over here. It doesn't look like anything has actually happened, right? When I look at doc, it's just the entire text. What's happening is every single word over here has been annotated now. For example, hundreds of people, so on and so forth. Each word, each token inside doc now has a lot of rich information. Let me show you. So we are now going to be, what happened just before was we'll be using this later. like doc. We'll be using the doc variable, the doc object later. What I wanted to show you, I mean, what the last 7 lines of code was how exactly you set up the doc object after you load up a pipeline and you run the code in. Now I'm actually going to show you the kind of things you can do using these docs. So I'm now going to run a bunch of experiments on smaller sentences. The reason is because it's easy for me to show you the results of these operations on smaller sentences. Once I show you the results of these operations, we're going to go back to using doc. But this is just illustratory. So last time what happened was we used an entire, doc was the entire newspaper corpus. Now we're going to go sentence by sentence. The sentences so sentence is equal to NLP, again, is my English pipeline of this is my sentence. And this is, of course, a lot faster. So the first thing we're going to see, which Spacey does, I told you a lot of things happen under the hood, right? A lot of annotations happen, a lot of information. What exactly? So one of the first things I'm going to show you is called post tagging. Post tagging stands for part of speech tagging. So in English, at least, for example, in a sentence, we have parts of speech like verb, noun, articles, and so on and so forth. Now, we can find what kind of parts of speech are there in our sentences once we finish passing anything through Spacey's pipeline. So here for token in sent, which is for token in sentence, I'm going to print the text, the part of speech, and the tag. So you can see over here, Tom went to IKEA to get some of those delicious Swedish meatballs. Swedish is an adjective, okay. But you can see over here that Tom, for example, is a proper noun, so it's marked as a proper noun over there. Went is a verb, so you can see it's marked as a verb. So you can see how just when we passed our text through Spacey's pipeline, we didn't tell Spacey to do this in particular, but Spacey has already annotated every single word, which means over here, every single word in all 300 of these documents in the example before has all been annotated with this kind of information. The part of speech, the original text, what kind of tag it is. As for, if you want more information about exactly what these tags stand for, I'm not going to get into details of that. I'd recommend you to go into Spacey's part of speech tagging documentation, which tells you what every single tag stands for. And then you can decide if you want to use it in your own work or not. But this is something very cool Spacey does. Along with all the other annotation, it has marked parts of speech as well. I just want to stop and ask if there's any questions or if everything is clear so far. Yeah? Yeah.
So you apply lower incorporate before? This is just NLP already applied or?
I'm just going to try and, for example, I mean, so your question is.
So here was a capitalized.
Yeah.
But earlier when you applied the pipeline to adopt partners, you are explicitly asking keywords.
Yeah. So the reason I did it to lower, so normally Spacey does not do it to lower. I mean, Spacey can tell you if it's capitalized or not, but Spacey doesn't. The reason I did to lower before, and this you will understand later, is that there's a bug right now in Spacey's current version, which means that if a stop word starts with a capital letter, it is not caught as a stop word. For example, a word but, if it's a capital B, and which is normally a stop word, it will not be caught as a stop word. So the reason I do lower is to make sure that everything is caught as stop words, but also because in that example for doc, I would later be showing you results of topic modeling, where it doesn't matter if it's capitalized or not. So in this particular case, because I'm just illustratory sentences, I'm not making it all into lowercase. But normally, depending on the kind of text analysis you want to do, if you want to do an exploratory text analysis where you just want to learn about the nature of your text, it doesn't really matter if your word is a capital letter or not, unless you're looking for the number of capital letters in your text, in which case, different ballgame. But normally, it really depends on what your end game is. In the previous example, my end game was topic modeling, which I'll talk about later. And in topic modeling, punctuation and capitalization does not matter, so I made it lower. But normally, Spacey does not make it into lower because Spacey annotates the words as they are. Is that clear? Okay. So that was post tagging. What we're going to be doing now is something called NER tagging. NER stands for named entity recognition. So in this particular case, named entities are, for example, if you would say that Emmanuel Macron is the president of France, Emmanuel Macron is a named entity because there's only one Emmanuel Macron who is the president of France, so it's considered a named entity. And president is an entity where there's many possible presidents. You can have president of the golfing club or whatever. You can have many kinds of presidents. So this is not caught as a named entity. Named entities can be geopolitical objects. It can be places. It can be companies, time. If it's a particular time, like 4 p.m. on Thursday, now that's a particular named entity. So named entities are, well, as the name suggests, they're named entities. But you can again, I would recommend going to Spacey's page and searching up what exactly named entities are and how it might be useful to you. This is actually a huge part of natural language processing research. A lot of people use named entities. You can imagine, for example, if you're building a chatbot and if someone says, I need to book something for something, it'll be important to find named entities in your text. So this is just a possible way where it could be useful. Again, Spacey does all of this. The one time we ran this, Spacey already has information about your POS and your NERs and everything. I'm going to give you an example. So you can see for 3 of them you have Tom, which is a person because that's a particular person. IKEA is an organization. And Swedish is an NRP. I'm not sure exactly what. But I believe here it's named. Hold on. Okay, so it says nationalities or religious or political groups. So Spacey has correctly identified Swedish as an NORP, which is named entity or religious groups. So this is what I mean. You can go to the Spacey linguistic features page, which is again not loading because the internet's not so nice. But yeah, you get the idea. I mean, you do get the idea, right? That's clear. Okay. Yeah. Okay, is there a question? I'm sorry, could you speak up? Maybe, can you pass over the mic? Thank you. Okay, I mean, now I've sort of already asked him to do it, so...
The texts which are not tagged, like this delicious meatballs, are they stopwords? Or what?
No, they're just not named entities.
Okay.
I'll give you an example. So you can notice that over here I did for token in sent. So I actually went through every single token in my sentence, and then if this token had a named entity tag, I asked that to be printed. But over here, I'm doing for ent in sent.ent, so it's for entity in sentences entities. And the only 3 entities in this sentence are Tom and IKEA and Swedish. Another really, really cool thing about Spacey is it has very nice JavaScript-based visualizations called Displacy. And you can import Displacy as part of your... it's a module in Spacey. And you can do cool visualizations. It's not as cool with named entities because, this is what it does, which is still fairly cool, I suppose. But you can do even cooler visualizations using Spacey. So I would recommend checking out Displacy later. I'm going to show you a small while later right now. But so when you look at computational linguistics as a field in general, there are certain things which are considered for example, part of speech tagging, NER tagging, and dependency parsing. I would say these 3 are the pillars of computational linguistics. And largely in text analysis, I would like to break up text analysis maybe roughly into a more statistical learning part of text analysis, or natural language processing part of text analysis, and computational linguistics part of text analysis. So far what we've seen with part of speech tagging and NER tagging, this is the computational linguistics part of text analysis. Just a note before we go ahead. So dependency parsing. Dependency parsing is really cool. As the name suggests, we're going to parse our sentences and identify the dependencies or the relationships between words in one sentence. So between the words in a sentence, how are they related to each other? Subjects and objects and so on and so forth. Now, dependency parsing in itself is a huge linguistic there's a lot to study in it, so I'm not going to get into details of what exactly it is. If you think it could be useful for yourself, please get into the research behind it. It's actually very, very neat. But just to give you an idea of what it looks like. Here, what we did was, it's Tom went IKEA to those Swedish meatballs. You have n-subj, p-obj, and p-ob. Here it's the subject and the object of the sentences. So here Tom is the subject and the object are his delicious Swedish meatballs. So that's how the sentence is broken up. Now, for me, when I normally work with dependency parsing, this kind of information is not only not very pretty, but it's not very useful. It's kind of tough to wrap your head around it unless you already know what dependency parsing is. And people do, people get degrees in linguistics and study dependency parsing. So it's sometimes difficult to understand this. But Spacy renders this pretty well. So over here, you can see, so just some information, Spacy makes this, this particular image using the information from here. So we use this information, and you can learn to interpret this information better later. But so what happens over here is, in dependency parsing, verbs, the verb or the action is the root, and everything else is linked, because you would say Tom is a subject, which is doing the action on the object, and so on. So over here, there are two verbs, get and went. So these are the two cores of the sentences. So again, this is just to give you an idea of the things you can do with Spacy. I'm not going to explain what dependency parsing is, because that's really another tutorial. But this is just to give you an idea of the kind of things you can do. And you can also create your own dependencies and your own meanings. For example, if you could also create dependencies for adjectives. If you'd want a graph like this, which says delicious Swedish meatballs, if you want delicious to be linked to Swedish meatballs as, it's providing information to it, you can train your Spacy model to perform this custom annotation. So there's a lot you can do regarding dependencies and relationships between sentences. This dependency parsing, there's two kinds. One is dependency parsing, one is constituency parsing. Constituency parsing breaks your sentence up into verb phrases, noun phrases. So basically this is linguistics. This is the linguistics part of text analysis, and I want to expose you to this so that in case, even if one of you finds this useful later, you can go back and do it. I would also recommend checking out exactly what Spacy's guidelines and annotations are for these particular linguistic operations. So, there's a lot of information. We have information about parts of speech, named entities, dependency, all of these dependencies in that one line of code when we ran it through the pipeline. So you can see why I kept going on and on about why I think this is the coolest thing in the fact that the sixth Jupyter cell, I think it was the sixth Jupyter cell, which actually ran my text through the pipeline. When we did that, we have all this information. So is that clear? Is everyone on board? Is there any questions? Anyone wondering why I'm doing this? Anything? Yeah? Cool? Awesome. Just a note, you would have noticed that over here, in the examples of part of speech tagging and NER tagging and dependency parsing, I want my whole sentence. I want my whole sentence because I want relationships between my sentence, and I don't want to really pre-process. I want to understand my entire sentence. But many times when we were doing text analysis, we want to run machine learning or statistical algorithms on our text. When we're running statistical algorithms on our text, I talked about stop words earlier, and we had a question about say and said and saying and so on as well. And there's basically cleaning. Cleaning is involved when we're running machine learning algorithms. The reason, for example, I'm going to very soon talk about topic models, so I'm going to use this time to briefly introduce topic models. Topic models are a class of machine learning algorithms which allow you to identify topics in text. For example, imagine you are all running, not all, but why not? You're all running newspaper agencies, and you happen to have 10 or 12 years of newspaper articles in online format, and you have the person who was in charge before you obviously did a horrible job and hasn't annotated anything, and you have no idea. This is completely unstructured text. So if you want to try and understand completely unstructured text, it means you cannot do your clustering algorithms as well, because it's just kind of messy, and of course it's not classified. So if you want to try and figure out what underlying themes are going to be present in your text, topic modeling is a good approach. For example, in the context of newspapers, what kind of topics would I expect to see in a bunch of newspaper articles? Maybe politics, sports, weather, and so on and so economics maybe. So when I expect to run a topic modeling algorithm on a newspaper corpus, I'd want to see these kind of underlying topics come out. Now, just a little bit more information about topic modeling. We don't name the topics ourselves, and we don't give any information to the algorithm apart from the number of topics. What we get is a bunch of words which have a high probability of occurring around each other. For example, if you are running it on American news in 2016, which is the elections, you might have maybe Hurricane Katrina, I think sometime around then. So you would have news about a hurricane, which would be one topic maybe. You'd have news about the elections and Trump and Hillary in one topic maybe, and sports and so on and so forth. So you would have topic 0 with a bunch of words which occur in high probability. All of these words would have to be to do with one particular topic. So you want to identify topics in text. And so why would you not want stop words in your topics in text? For example, imagine we had a topic which was A and the went go. And this is not providing any information to me about my corpus, which is why you'd want to get rid of stop words in the first place. And as for the question which you asked about how the spacey, one thing about the word say, said, and saying, and so on and so forth, what you consider a stop word is really up to you. There is no official list of stop words. There are suggested list of stop words. And even in different domains, like if you work in biology or different kinds of domains, you'd have a different list of stop words. Now, the way spacey annotates stop words is not through the root of the word, but through the word itself. Now, another part of pre-processing, which I'll get to immediately, is something which we call lemmatization, or so basically what lemmatization is, it gives you the root word among the word which you're using. So for example, in the example of say, said, saying, and so on, I would only want the word say. Because, for example, again, if I have a topic with say, said, saying, not really getting much information. Now, if I can condense all that into one word, a root word, say, this is useful for me. But the way spacey marks its stop words are, it doesn't think that say is a root stop word, and all the words which come from say are stop words. You'd have to say that all of these words are stop words, and they so happen to have the same root. But you see now why I had to actually individually catch out every possible variance of the word say and mark them as stop words. Because while spacey does know that the root of all of these words is say, it does not take that into account while deciding stop words. Is that clear? Okay. So I talked about topics, and I talked about why we'd not want stop words in our topics, right? Let's think of other things which we might not want in our topics. We probably don't want punctuation, like we don't want full stops and commas and colons. I do not want numbers. And in this particular case, I also don't want I'll explain that later. But in this case, what I'm going to do right now is I'm going to only use important information from my text to generate my corpus. This particular bit of code is very, very important. So if you do not understand why we're doing something, please stop me. What I want to do is I want to create a corpus which can later be used for machine learning algorithms, right? So you can see over here that what I'm doing is, if you remember the original structure of the data set, every new line was a new document, right? So what I want to make sure is the moment I hit a new line, I want to store a new document. So you can see the moment I see a new line, I append my article to my entire text, and I clear out article. I see some slightly confused faces, so I'm going to go over this again a bit slower. Let's look at what's going on. For W in doc, which means that for every single token in my original document, what is doc? Just to give you a quick reminder, this is doc. So for W in doc is literally for hundreds of people. So I'm going through every single word in my document. So for every single word in my document, if that word is not a new line, if it's not a stop word, if it is not a punctuation, if it's not a number, and if it's not I, again, which is not caught as a stop word, then I want to add that particular word to my corpus or to my data set. Yeah? So lemma. What you see over here, lemma, is the lemmatized version of the word. Yeah, so again, this is actually a spacey bug, which I just figured out yesterday. So what happens is its lemmatized form of the word I is considered as pronoun. So for some reason, it was messing up the results. So I basically made, and again, I know for a fact that I is not important information to me. So I particularly catch I over here. So this is more like a bug. I mean, it's I'm just trying to make sure that I don't catch I. Yeah? Oh man, your app. Bam. So again, since you do point it out, normally the reason I had to do that was I is caught as a pronoun when spacey finds a lemmatized version of the word. So I was trying to avoid that bug in my code, so I took out I, but then I forgot I actually made it lower in the whole place. You're just never going to catch that. Wonderful, thank you. Okay, so let's get back to what is going on. So if it's not a new line, if it's not a stop word, basically if it's not what I consider useful information to me, stop words are not useful information, numbers are not useful information, punctuation is not useful information, then I'm going to add that word, but not just the word, the lemmatized version of the word. What does this mean? This means, like we talked about before, words, I'm just getting the root. For example, again, I used say, so I'm just going ahead with it, but saying, said, say all have the root word say. So I don't want to add a different version of the word every time I come across the same semantic meaning, so I add only the root. This root is called the lemmatized version of the word. There's another way to do this. It's called stemming. Stemming basically like just hacks off the last part of the word, but it's kind of ugly and damaging, and I don't like it. So again, this is a personal preference. I think lemmatizing look is prettier. I like my text analysis results to be nice and pretty and clean. So that's what I use. But you can use stemming as well to do your word cutting. So what I do over here, and then after that, if I do find a new line, it means I've reached the end of my document. So I'd want to start doing the same process for my next document, which is why I append my article to my text. Text is a list, which you can see I've initialized in the beginning of my Jupyter node, in the beginning of the cell. And I make article again empty, so I can start collecting words in my article. Is this very clear? And why we're doing what we're doing and how we're doing it? Well, to be fair, this is actually, you mean for pre-processing text? So the reason why there's no helper function which does this exactly is because people pre-process text very differently based on what they want to do. It is really impossible to say. Some people might want numbers, for example. So in that case, I would just remove the numbers part. Some people might be, for example, there is actually research on the way stop words are important in, for example, in the style of an author, in which case I would want stop words. Some people would consider stop words to be the absolute basic part of pre-processing, but in some cases you might actually want it. So what's happening over here, for example, it looks like a lot, but I'd like to remind you this is like literally 5 lines of code or 4 lines of code. And before this, my doc is equal to NLP of the sentence is again 1 line of code. If you use NLTK, for example, to find pause tags, verbs, stop words, numbers, punctuation, you would have 30 lines of Python code. 30 lines of Python code is a lot of code. So here in roughly 6 or 7 lines of code, I'm cleaning my text completely. Also, I'd like to point out that in some cases, you might want your topic models to have no verbs. In which case, I would get rid of verbs using the pause function before. So I have a lot of information with me right now. The way I'm using this information is I'm using these parts of it, but you can run, once you've passed your text through your pipeline, you can do a lot of cool things with it. This is just one of the things I'm doing. Yeah?
How would you handle abbreviations for words in this example?
Okay, so it depends on, when you say handle abbreviations, you'd want to get rid of them, you'd want to include them, you'd want to...
I want to actually process them. I don't know if you handle, let's say, tweet analysis, so people are not writing the whole word, but rather abbreviations. So how would you include that in your, because if you're doing newspaper analysis, of course you're writing, let's say, proper sentences, but in tweet analysis, you probably do it differently, right?
Yeah, so tweet analysis is like a very different ballgame in the sense that you'd have to, again, when it comes to things like this, you'd have to be very particular. For example, when you say abbreviations, you mean like any kind of, like et cetera, any kind of slang. So you'd have to write code for that. Spacey, so just for information, like Spacey has pre-loaded models for different kinds of things you'd want to do. So if there's something in particular you actually want to do, there's likely a Spacey model which handles that particular thing. Or if you really, really want to do it and it's a business, you can actually pay Spacey to download a model to do it. I mean, I'm just like, or you can write code to get around it. So you'd have to write your own hack to get around it because it's not a super common thing. Like in traditional computational linguistics wasn't, I suppose, built for slang. Slang in general is tough to catch. But there's a lot of spacey models which catch particular things. So, and it's also not super difficult to write exceptions or write added functionality to your spacey pipeline. It's easy to add new pipeline functionalities. But for your particular case, I'm not sure. I've not worked on that, particular part before. So just to give you an idea of what text looks like. So you saw before the doc, right, which had all the words. So now if you've noticed, it says 100 people forced vacate home, Southern Highlands. So you can see all the words which I believe have had no meaning, like I, am, the, and all stuff like that have all been removed. This only contains useful information. So texts is a list of lists where the inner lists are each of the documents with the words, non-important things removed, and of course split up. It's not a string, it's each is a separate word, and all of these lists are put together in my massive list, which is my final data structure. Is everyone, you have an idea of what this data structure looks like? A list of lists with words inside it? So I'm going to talk about, now we're going to be using Gensim for the first time. Gensim is the, oh God, half an hour. So I talked about using Gensim, and what's the first thing we're going to do using Gensim? We're going to be making bigrams. Bigrams are basically, in some cases when we're dealing with large bodies of text, some words tend to, or collocations, these are called collocations or bigrams, some groups of words tend to make more sense together. Like New and York, for example, it just makes more sense as New York. So one possible way we can do this is using Gensim's phrases module, which creates these bigrams for us. I'll give you an example which is more relevant to this particular data set. For example, this was 2000 and 2001, okay? Which meant that, yes?
If you be so kind and scroll up the slide, because when I'm looking at the output of text, it doesn't contain any articles anymore.
Yes.
Where they have gone, because when I'm on the right, scroll up again a little bit, I don't see any comment. No, it was up. I don't see any comment telling me, please forget about any articles. I just see forget about punctuation, the stop words you have to find somewhere.
So,
Which just contains mainly set.
so articles are stop words.
And so they are predefined, this package? Or?
Yes. So the thing is, articles are stop words because stop words are any words which do not add useful information. So a and the do not add any useful information. Please go ahead.
Can you imagine of any scenario where articles could be interesting?
Of course, there's a lot of cases in which case it's interesting. In which case, for example, articles are also a part of speech. So you can just write one extra line of code, which would be, but if it's an article, put it in the code. So this really depends. For example, if for your particular analysis, articles are useful, so do not remove them in the pre-processing. But normally and traditionally, in all cases of text analysis, articles are considered stop words. No problem.
Sorry. If two stop words are just reference to something else in the text, like A and B are something, and then you remove it, then you lose some information. How do you deal with it?
So, for example, you said if the stop word refers to something else, right? But I'm not removing what it refers to. I'm just removing the stop word.
Yeah, but then you lose the connection. So A and B are very nice cities, but then you remove A and B, you lose.
So, okay, for example, do you mean like in New York, new, if new is a stop word and then I get rid of new, then York doesn't have any information? Do you mean something like that, for example?
You write in the text A equal a city, B is equal another city, and then later you see A and B are one of the city. If
Okay.
you remove A and B from the sentence, you lose information.
Of course.
But then how do you do it?
You don't remove the words from the sentence.
But then you have a lot of other stop words that are not useful.
So if you want a particular stop word to be removed or not removed, you can, like I've done in the sentence before where I did for say, saying, Mr. and so on, you can like hard code spacey to consider words as stop words or not stop words. There is no one universal list of which stop words works or not. For every project, you keep adding or removing stop words based on the results you want to see. So if you feel that certain words are going to be useful later, like if you see there's a semantic relationship between a capital A or a capital B and a particular entity, then you just have to be very careful in your code to make sure that you don't get rid of that on accident. Yeah, so I talked about bigrams. Bigrams are basically words which have more sense together. So in this case, this is how I make my bigrams. I'm going to do this a bit faster. So text is equal to make bigram of line for my line in texts. To give you an example of what happened, earlier on over here, New South Wales, right? But New South Wales is a state in Australia, and it makes more sense if that was considered together. You can see over here, New South is one word. So this changes your dictionary. Is this clear? So basically, words which tend to appear more often together are caught together. And this is done using probability. Yes? So in that case, what you would do is I would do, if I basically run bigrams again, it becomes trigrams. So in this case, I'm only looking for bigrams because I'm doing 4-line in text and it's a one-phrase model. If I want to be sure to catch multiple phrases, I would run it again. You can have 4 grams, 5 grams, n grams, basically. In this case, just to give you an example, it's 2, so it's New South, and so on. So another thing to remember is that, of course, for most machine learning algorithms, I mean, in fact, all you cannot feed a raw text as your input to any algorithm. You would need to convert this raw text into a vectorized form so the machine learning algorithm can deal on vectors. Again, when we deal with any kind of machine learning algorithms, we use vectors or numbers and not words. So we need to convert our, basically this list of lists, which just has words, into something more meaningful which a computer can understand. An easy way to do this is to just create a dictionary. So, oh, come on. So to give you an example of what exactly is going on under the hood over here, corpus of 0, for example. So what I'm doing is I'm converting just my words into something you call a bag of words representation format. There are many ways in which you can represent words in a way which computers can understand. A very popular way is something called bag of words. So what's happening in bag of words is you first get your IDs. Like if you based on, for example, in this particular case, this is our first text before we did any kind of transformation. It said 100 people, 4, so on. So we now map every single word to an ID. So 100, because it's the first word in our corpus, would be 0. People would be 1, 2, 3, so on and so forth. Now, once you have your indices, you do this. So what I'm going to do over here is bag of words basically says this particular index occurs in this document this many times. For example, the first corpus of 0, which is basically just the transformed version of my first document. Word ID 0 appears 1 time, which is why you have 0, 1. Word ID 1 appears 3 times, which is why you have 1, 3, and so on. So is everyone able to understand this particular format of representing my original data? It's called bag of words. There's many ways to do it. This is just one way. Is this clear? Because it's extremely important that you know what your data is supposed to be represented like, yes?
Can you say what exactly dictionary does?
Oh, yeah. So what dictionary does is it basically, based on your text, it goes through every single word in your text and assigns an ID or a mapping to it. So every single word now has an ID. So, I mean, I could do people, 1 and highlands, 3 and stuff like that, but I don't want to, computers don't have to deal with words, right? So because I want the computer to only deal with numbers, I have 0, 1, 2, 3, so on and so forth. Yeah? A list of lists is what you would want it to be. Also think of it, which other kind of format would make sense. Yeah, so list of lists is basically, again, it doesn't really make sense. So for example, usually for example, if you're dealing with tweets, someone mentioned tweets, the popular thing. Each tweet would be one list and you would have a lot of tweets, so that's one massive list containing a lot of tweets. I don't see which other data structure. Maybe you could have, basically you would need any streaming data structure. It doesn't need to be a list. Like if it streams one by one, it'll work. I mean, if anyone thinks of any other data structure they can use to represent it, you can stop me. Maybe NumPy arrays, which contain words, whatever. But you would need something like that, right? So is this clear? Because, yeah?
Can you convert this back to the text?
Yes, you can. So what I've also done is I don't want to destroy my original text. So you can notice I've done dictionary is equal to dictionary of texts, and I have a new variable called corpus, which contains text. So I'm not damaging text. And what I'm doing is dictionary.doc2bow. Doc2bow literally stands for document to bag of words. So I'm doing document to bag of words of texts. What you can do is you can actually go back and you can reverse ID. Dictionary of one is this word. But it's just a pain. I mean, I would just not break my text and I would keep the rest of the things.
I just want to understand the second line, for example, 1, 3, what's the first word?
Yeah, so you do dictionary of one and then you'd find out the word is people or highlands or whatever it is. Yeah, I've just kind of, you can see dictionary of one, for example, is Sydney. So you'd have to, of course, write some code which goes through every single thing and then makes a loop and then prints it out. It's a pain, which is why I didn't destroy my initial thing, but this is what it looks like. So the first thing, I talked about topic modeling before and what exactly it is. So this is our first topic model, which is called LDA. It's a popular topic model, 2003. Really nice paper, too. You should read it if you like science papers. But it's a lot of fun. It happens quite fast. Now you're going to see what... So I just want to show you what a topic model looks like. Over here, I created my topic model. I just did LDA model. I called LDA model from GenSim. I passed my corpus, which is my data after it's been transformed into the way the computer understands it. I said I want 10 topics, and I said ID2word, which is, well, ID2word, is my dictionary. And I just gave this much information, and then after that, after around 2 or 3 seconds, it spat out these topics for me. So right now, if we didn't look at the Australian data set, and if you had no idea, we would have really no clue about what's going on under the hood, right? Like what's actually in my documents. Now you kind of have an idea. If you'd say there are 10 topics, one topic is about a fire, and you can see there's actually a lot of fires happening in Australia in that time. So you can, okay, a lot of them here about fires, but you can see topic 5 is union, force, government. So you can see maybe there's something about, people protesting or something. Then you have Israeli and Palestine being a problem in 2000. So you have to remember that I did not fine-tune the results of my topic model. This is illustrative. If you'd want an ideal topic model, I would run it many times. I would, you can, so when you can go back and read the documentation for LDA model, but there's things like passes, runs, where you see how many times you want to run it and fine-tune your model to get better results which you want to see. At this point, this is just illustrative to show you what kind of results you get. So the kind of results you get is 10 topics, so you have topic 0, 1, 2, 3, up till 9. And you have in that topic, what are the most likely words to appear in that topic. In topic 0, the most likely words are fire, Australian, people, so on and so forth. Topic 1, and so on. You can see over here that it looks like some of the topics are repeating themselves, in which case, choose a number of topics to be 5 instead of 10. So this is the way you bug your topic model. You look at it, you're satisfied or not satisfied, and then you make changes to it. I'd like to point out now that in my GitHub repository, which I was talking about before, I have a tutorial on topic modeling, where I talk about what exactly topic modeling is and how to get better topic models. So I'm not going to go into details about how to get a better topic model, and I recommend you having a look at my other tutorial. But so what exactly a topic model is, based on the text which you passed, creates topics based on the number of topics you asked for, and it basically assigns probabilities of words appearing in that topic. Later, you have documents which are made out of topics. For example, if you'd find a newspaper article which talks about maybe Australian fires, it would be 94% topic 0, 4% topic 1, 2% topic 2, for example. So you can find out what percentage of topics are in your documents. You can find out what words are in your topics. And using this, you can cluster your documents, you can arrange your set, you can have a broad view of what exactly is in your data set. You can do a lot with topic models. About what exactly you can do with topic models, check out the other tutorial. This is just to give you an idea of what topic models are. Yes?
How can you evaluate basically the performance of your topic models?
This is a very nice question. How can you evaluate the performance of your topic model? Well, the thing is, because this is something very subjective, it's difficult to evaluate it. So there are some measures, which one is what you call topic coherence, which basically means how coherent a topic is to a human. So there are algorithms which try and estimate the level. What you can also do is you can actually visualize your topic models and see if it makes sense in terms of the proportion of words available. So I actually have an entire section on evaluating topic models in my topic modeling tutorial. So if you want to see the exact ways I do it, you can check it out. But it's a bit shaky, I'll be honest. Like even the top research papers in the field is like, we're not sure. So I'm going, yeah? Yeah, so yes, it's the probability. So the thing is, for example, in topic 0, there is 0.006 chance that the word fire would appear in that. Now, this may not look like a very high probability, but you have to remember that the entire corpus is... So there's 5,329 words. So considering that, that's quite a high probability of that word appearing in that topic. Well, not 6, but 0.6, but yeah. Okay. Yes, absolutely, yeah. Yes?
Does the corpus originally write about one topic? We chose 10 topics, but is it originally just one?
The original corpus, I would say, briefly from my experiments, might be 3 or 4 topics, roughly. Like I would say one, there seems to be a lot of fires going on in 2000, so that's like one massive topic. There's the Israeli-Palestine conflict. There's something about Al-Qaeda also coming up. I think you might find it here. Then I think there's a cricket topic. I mean, these are just news. So the thing is, to be honest, this is not a great topic model in terms of how useful it is, but it also took around a second to run. So I put almost 0 effort into tuning my topic model. So tuning your topic model requires, based on the size of the corpus, like having multiple runs, making sure you set your corpus up for you to get good results. So as for how many topics are inherently present in the corpus, I would say maybe 5 to 7, but then you cannot really say. There's no ideal number of topics. So it's more of a broad theme. Also remember that this is a probabilistic algorithm, so each time you run it, the results are different.
So one part of the tuning is that you tune the one that you start with.
100%. 100%. So all the questions which I've been asked so far, more or less, have actually been covered in the topic modeling tutorial, which is in the same exact repository as this tutorial. So you would actually be able to find out more about it. And it's really interesting. Topic modeling is one of my favorite parts of text analysis. Because just to note that this is completely unsupervised. The only thing I passed to my model is my corpus. I gave 0 information about it. So there's a lot. It's really powerful. You can do a lot of cool things with it. Just a note, I have only 20 minutes left, so I'm going to kind of hurry up. So I'd appreciate it, unless the question is extremely pressing, if you could ask me after the tutorial, because I'm going to be hanging around here. So just note the question down, because I have 20 minutes left. Text classification. How is this different from topic modeling is that when we're dealing with text classification, or just to give you a heads up, the first 2 things we talked about was cleaning your text, then computational linguistics, and then topic modeling. So I'm going to continue doing this, briefly introducing topics and going on. About text classification, when we were talking about topic modeling, our data set which we used, which was the Lee corpus, had no annotated information. We did not know, like the question just asked, how many possible topics are there? We had no clue. It was no information whatsoever. But in the cases, a lot of people here who worked in classification problems, you have examples of a certain amount of classes, you have examples of text which belongs in those classes, and you would want an unseen text to say, oh, it belongs in one of these pre-existing classes. So that's what classification is. You have a bunch of classes which you already know, you have data which is already annotated, you use this annotated data with these classes to create information of what possible new text could be in which class, and you classify that. So this is another thing which you can do with text, which is classify it. The data which we're going to use over here is something called the 20NG dataset, which stands for 20 news groups dataset. So it's again a mix of articles which are broadly broken up into 20 different groups. I'm only going to use 4. Excuse me. And these 4 are atheism, graphic space, and miscellaneous. These are again like completely random 4 topics. Well, not completely random, but random enough, I suppose. Okay, yeah, I'm just getting my imports. A few lines about what's going on over here. Data train, so I'm fetching my data set. Now, some of the things which I want to just briefly talk about, because I'm going to really run through this. I'm sorry, I apologize about that, but I don't have much time. Okay, number of components, 5. What this means is that I want to, hold on. Yeah, I want to basically reduce my number of dimensions to 5. I'm going to explain that in a second. Labels is basically my the values from my data set already classified. True values are the actual values. Okay, so just to give you, before we talked about, for example, in the previous data set, the size of the data set was 5,639 words. So when you have 5,639 words, when you want to build a traditional classifier, the classifier actually, looks at the presence or absence of every single word in your document and then makes a decision whether or not that word exists. To give you an example of where text classification is used every single day, it's in spam detection. That's a kind of classification problem with text. You have spam or not spam. So based on the presence or absence of certain words, you usually train a machine learning model to predict whether a new document is going to be spam or not spam. I mean, for example, in spam, you would have winner or, like bank or enlarge or so on and so forth. So, you have certain words which appear more often than others. Presence of these words means bam, you're spam, not presence means. But the thing is, with 5,600 words, it's actually not so many words. Larger corpuses have like millions of words in them. So how do you deal with that many words? How do you build a classifier which can actually tackle this? You can try and reduce the number of dimensions where you represent your 10,000 words or a million words in less dimensions. In this case, that's 5. Why I chose 5 is because the scikit-learn documentation said choose 5. But honestly, you can spend your time and find out the number of components you'd want. Again, this is a game where depending on the size of the corpus and depending on certain specifications, you would choose it. I think I saw a hand go up, yeah?
Can you say how many words you need for classification?
How many minimum words you would need for a classification? I'm not sure, but technically a machine learning algorithm can work with 2 words. I mean, technically, it just would be a very, very bad, maybe 5,000, I would say. But then again, I'm like, honestly, I'm just kind of winging it. But of course, just as a usual ballpark, like more words are better, too many words gets messy. I mean, it doesn't sound like great advice, but that's how it is. Vectorizer. So what my vectorizer is, initially I talked about how computers cannot understand words, so I vectorize it, which basically means I convert my words into numbers. You might notice I've written TF-IDF vectorizer. TF-IDF, previously we used bag of words, right? We use bag of words to represent the number of words which we have. So I basically used a bag of words to represent the number of words I have in my document. TF-IDF, it stands for term frequency, inverse document frequency, where it based on more words in document means that word is represented more. If this word appears in a lot of documents, means it's not so important. I mean, I'm kind of rushing through this again, but TF-IDF is basically a way you can represent your words to a computer. So you can maybe search about it and find out if you want to know more about TF-IDF. It's just a way to represent words. So I'm vectorizing it using that. Xtrain fit transform basically means I'm transforming my data to the specifications which I mentioned before, which is my vectorizer. Then SVD stands for singular value decomposition, which is a matrix. Where's my damn mouse? Yeah, which is a matrix factorization method, which basically reduces the number of dimensions. I mentioned 5, a number of components, so it happens. Then I normalize it, and LSA is again another part of this pre-processing step, which stands for latent semantic analysis, which basically creates your number of dimensions. So I know that I'm aware of the fact that I really rushed through this. Just some of the keywords I used, TF-IDF, which you should probably search up, SVD, and LSA. What I'm doing using TF-IDF, SVD, and LSA is basically reducing the number of dimensions I have to a lot less, to a better number, so that it's easier for me to build my classifier. These are considered standard pre-processing steps when you want to build a classifier. I would recommend, if you want to know more about each of these single ones, to search about each of those single ones, or just talk to me after this is over. So now I get my data, and I am going to, I'm extracting my features. So all of this, what you saw until now, was actually just my setup. I basically just vectorized, set up my data. Like you saw the pre-processing I did before, that was manual pre-processing. The reason I showed you that is to show you the amount of control you can have with your pre-processing. Someone also asked me, isn't there a helper function to do this? Yeah, these are the helper functions. So I did absolutely nothing. If you might have noticed, I didn't remove stop words. But when I'm using stop words English over there, I don't know if you can notice this. Over here, yeah? So it's happening. So there are helper functions to do it, but I wanted to show you how Spacey gives you the power to really play around with it. You can hurry up and do scikit-learn, and other packages have pre-ways to sort your text out. So what am I doing over here? I initially talked about the spam, not spam. One of the earliest algorithms for this spam, not spam was Gaussian naive Bayes, which is a kind of where you kind of use the probability of the word appearing in a document to see if that word is spam or not spam. So it's not super complicated probability and statistics. It's actually really fun if you get into the details behind it. I'm going to recommend you to Google it. So here we go. What's going on over here? So the second classifying algorithm is something called SVM, which is support vector machine, which is also really, really fun. It kind of splits our data into a different dimension space where you can kind of separate into different classes. So these are the two kinds of machine learning algorithms. These are probably the two most popular basic classifying algorithms. So what we did before was we set up our TF-IDF vectorizer, reduced our dimensions, made sure data was ready for the algorithm. Then we trained our machine learning models, which here was one model was the Gaussian naive Bayes, the other model was the support vector machine. And once we've trained our models, after we transformed our data, we make our predictions. So what you can see over here is 0, 3, 3, so on, means the first document was classified into class 0, second document into class 3, and so on and so forth. Yeah? So that's a lot of information I just threw at you folks. Is everyone okay? Any hands going up? Anything you want to ask me? Yeah? No, they're very different. That should have been clear. Okay, so I'm going to let you finish. Yeah. Okay, I'm just going to clarify this because it's very important. You might have also noticed we used two different data sets. For topic modeling, we used the Lee corpus, which I was talking about with all the newspaper information, and it was unlabeled. We had, like you saw before, there was absolutely no information about the corpus. I want to find out things about my corpus, so I used topic modeling to look for maybe hidden structures which happen to be my topics. In text classification, we are very aware of the classes. In this case, it's atheism, miscellaneous, graphics, and space. We are aware of these four topics. We have 4 classes, We're aware of these 4 classes, and we have a data set which has documents with these classes annotated, and we have documents where it's not. So we are training, first what we do is we transform our data to a way it can be understood, and after we do that, we train a classifier which learns what kind of words are more likely for it to be in one of these 4 classes. It looks at a new document which it does not know, and then based on this information, it puts it into one of these 4 classes. So we know what the classes are. It's a labeled data set, and our problem is rather fine-tuned. There's a certain thing which we wish to achieve, and which is put this document into a class based on labeled information. Topic modeling is different because you really don't know anything, and it's more exploratory. So again, like I mentioned before, what we started off was computational linguistics. Pre-processing, computational linguistics, topic modeling, text classification. These are all related but completely different tasks. Again, like I mentioned before, I want to give you more breadth than depth. I want to give you an idea of the different kinds of things. These are all quite different things. Yeah? So the last part of the tutorial is going to be, so again, just to clarify, these are 3 separate tasks which we did, and now we're done with them for now. And now we're going to do deep learning, which is the final part. I would like to mention that there's 7 minutes left, so I'm really, really going to run through this part. I would have liked to take more time, but you are more than welcome to stop me afterwards. Just honestly, if you download the tutorial, things should be pretty easy. But right now, it's going to be really, really fast. Yeah? So, Deep learning. Deep learning basically stands for machine learning, which uses neural networks, and we're using neural networks which have lots of layers. Because they have, well, lots it's quite arbitrary, but let's say more than 8 layers, roughly, you would call something a deep learning algorithm. So again, deep learning would be very roughly machine learning using neural networks, lots of layers, deep learning. Kind of. Again, these definitions do vary, and you shouldn't take my word 100% for it, but this is roughly what deep learning is. Just, by the way, there's also shallow learning. That's actually a thing, and it's also very cool for text. But right now, what we're going to be doing is using deep learning to try and generate text. What I mean by generating text is we have access to text documents before, and you want to try and mimic this text or generate text. The best way to do this is using a kind of neural network called a recurrent neural network. And in recurrent neural networks, there's a particular kind called LSTM. LSTMs, which stand for long short-term memory, are useful because when we want to generate text, what's really important is context. Long short-term memory has the ability to understand this context, and based on words which have appeared before, and we try to predict what are the odds of a certain word appearing next, and you predict this word. By predicting words, we're generating text. So it can look like a machine is actually writing like, for example, if you train it on Shakespeare text, it's going to look like it's writing Shakespeare. I cannot recommend these 2 blog posts enough, Understanding LSTM Networks and the Unreasonable Effectiveness of Recurrent Neural Networks. They're about text. They're very well written. They explain the intuition of these neural networks and the things you can do with it. Again, could not recommend it enough. Please check my notebook and read these blog posts. For this part of the tutorial, we're going to be using the code from this GitHub repository. So it more or less follows the code from there. So honestly, at this point, because I have 5 minutes left, I'm literally just going to press enter. So I apologize. Really. Also because this takes some time to train. And I'm going to briefly run you through the code, so don't be alarmed. But it takes some time because... Yay, okay. Okay. Okay, super fast what's happening over here. First, I'm using Keras to get all my imports. I talked about LSTMs and sequential. These are basically... Okay, so the imports are basically the tools I'm going to be using to build my neural network. I want to, the next bit of code is for you to understand what exactly categorical or one-hot encoding means. Here we're basically going to say a particular document, we talk if it contains or does not contain a word by the presence of 1. So for example, over here you can see that there are zeros and ones, and based on the presence or absence of a certain ID, you have 0 or 1. It's basically binary encoding, which is the kind of encoding which this is the language the neural networks understand. This is the information which you'll be passing to the neural network. So neural networks itself, honestly, could be a tutorial of its own, or 2 or 3, technically a semester-long course. So I'm not going to get into details about exactly how neural networks function. Right now, you can think of it as a magical black box, which does cool stuff. But again, like I mentioned, the 2 blog posts I talked about before will kind of make these things more clear. But what I'm doing over here, there are some things which are important. One is drop rate activation. So what these exactly mean is sometimes for a particular data set, neural networks tend to overgeneralize, which means that they tend to work only well for that particular data set. When this is happening, we want to drop out, so we have things like drop rates. Activation here basically stands for when we get information and you want to activate each neuron, what kind of function you're using. In this case, we're using softmax, which is a kind of activation function. So these are keywords which are regard to the way neural networks are built. Again, like I said, I'm not going to talk about exactly how you build them. And the Keras documentation actually has does a pretty good job in explaining what each of these parts of the neural networks are. So these are the parts when I'm creating my model. This is what I'm doing. You can see over here I say input, and then I talk about my input shape, which basically puts my dimensions out for it. Then I've talked about LSTM. Again, LSTM, long short-term memory, good for building context. This is my basic model. Then dropout and dense basically talks about when do I want to drop out instead of if I'm overgeneralizing, and dense talks about the kind of neural network layer, in which case here is a dense layer. Pardon me. Now here we create our model using the information I talked about before. You have drop, active mode, number of dimensions, then you have a flag. And over here, so these are just basically the steps which I'm using to create my model. Again, I have a minute left, so I'm really not going to get into this. But then, as for training my model, you have a loss function. A loss function is, again, a part of the neural network which decides how it's trained. Same with their optimizer. These tend to be, so all of the variables, hyperparameters I've chosen here are kind of optimized for text generation. So you can kind of use the same hyperparameters for your experiments as well. And what I'm doing over here, this is the fun part. I'm going to actually talk about so once I've created my neural network, the actual text generation part happens over here. So I basically want to predict the next word given a certain bunch of words happening in the past. For example, when I talked about, if you're going to talk, for example, there's a bunch of, you can imagine there's a bunch of neural networks out there which try and predict what Trump says. So, predict is kind of complicated. What the style in which he talks like. But for example, if he says, and this is a character by character text generation model, okay? Now if you're trained on a lot of Trump tweets, if the first letter of a word which Trump starts with a capital S, it's highly likely he's going to say sad, right? So out here, now we know he's going to say sad because he says that a lot, but so does our neural network. So on seeing S, a capital S, capital one, because he always uses capitals for sad, when he says a capital S, it's likely that the next word is going to be a capital A. So now what we do is we get probabilities and we predict that the highest probability is for A, and we generate text based on what is the most likely word. What happens over here, so a lot of training which is going on over here which trains my model. And so, out of time, out of battery. So, but you can see over here because I'm training on. Yeah, it's back. Okay, really, really fast because this is like the last cell. You can see hat is all that we had hoped for. The videotape showed Bin Laden speaking to supporters in the room. Whoa, that's a bit dark. But you can see over here the reason it predicted this was because we are training on newspaper data based on Al-Qaeda and Bin Laden and so on and so forth. So it is pretty much writing its own newspaper article based on the newspaper articles it read. So that's what my neural network is doing over here. So this is the last example of my text analysis tutorial. Really, really fast, the things we talked about, the packages we're going to use, the importance of where you're getting your data from, how important it is to clean your text, computational linguistics, topic modeling, text classification, deep learning. These are a bunch of cool things you've learned about. I would really recommend checking this tutorial out in more detail later. I have a lot of reading material and stuff online as well. So I hope you fellas had fun.